Hi everyone. I would like to clear up some concepts, and I think this is probably what I'm gonna do from now on. Kind of go over the concepts together from the instructor book that I share as PDF with you on each class. So this is from Monday's class. It's page 2000, not 2000, 219. Kind of want to start from here. And now I just want you to kind of realize that those summaries are really important for you to double check your understanding. Okay, so I'm going to kind of start with that. Previously, what was covered is, for example, energy conservation. This was briefly mentioned so far. Okay, so we are still using it, but next chapter is all about energy conservation. It's going to be almost all about energy conservation once we cover potential energy and so forth. So, and again, we always write out the full energy conservation equation, then we simplify. I try to show that in quite a few problems so far, and we will be doing that in next chapter in even more detail. And to this chapter, this is still chapter 7, and this chapter focuses more on the work term in the energy equation. But we do relate the work term to the other energies, so we still need to use energy conservation. So to determine the work, what we do is we need a free body diagram still. Okay, we need to see how many forces acting on it, and then we look at if each force, if they do work. Okay, so I'm kind of going over this. And for a constant force, then the work done is easy. It's just F dot D. It's a dot product between the force and the displacement. So you need to, for the work term, to calculate work, I usually, on the side of the free body diagram, I show the direction of the motion to show my displacement vector. And then when I do the dot product for the work term, I can easily see what the relative angle between F and D is, so then I can figure out if the force is doing a positive work or negative work or zero work. So as I will be also solving again other problems, try to pick up that habit. I think it's very useful. And so the only component of a force along displacement does work. If you don't have a component along the displacement, or the force is just perpendicular, that means the force does not do work. Okay. Even though, like, think about this, you are carrying a really heavy, maybe grocery shopping bags or something, and your hand is on your side and you're walking, it's really heavy, or maybe you're holding a briefcase or something very heavy, just like imagine that, and you're walking and you feel it, right? It kind of is pulling you down, and it's hard to carry. It feels like you're doing a lot of work, but actually think about the displacement direction and think about how you're pulling the bag. So you're pulling the bag upward, and the displacement is, so if kind of I want to show that, if you're moving this direction and this is the bag, the force is upward, right? You're pulling it, so this is your force on that bag by you, so that's the applied force. And so you just need to look into those two vectors, and the angle is 90 degrees, so you're not really doing work. Okay, so it's not very intuitive sometimes, so it can be tricky. So just rely on the equation. F dot D becomes FD cosine 90 here, and that becomes 0. So then for this case, although you're walking and you're carrying that heavy bag, you're really not doing work in physical terms. Okay, so to get the total work, the sum of the we sum all the work done by each individual forces, and the work can be positive, negative, or zero, so you have to keep the signs, and then we can find the total work done. Or you can find the net force and then use that to find the total work. Okay, but usually in the problems, especially in this chapter, they're going to ask you to find the work done by gravity or work done by the normal force, the applied force, tension force, all those forces. So you probably already you already have the individual work done, so you just need to add them up to find the net force, net work. And the sum goes into the energy conservation. Okay, so we are going to again work on that. And hopefully in a few more examples it will be more clear. And there's no if there's no displacement, then there is no work. Again, think about this case again. You are holding a really heavy bag, but you're not moving. You feel like you are really like trying hard to hold the bag, and you're gonna get tired, but it doesn't mean that you are doing work. Okay, so you just gotta check the equation F dot D, F, D, or cosine theta, right? There are three terms. If any of those will give you 0, then there's no work. Not just 90 degrees, F or D could be also 0. And there was an example, like pushing the wall against, I mean, you're applying a force against the wall, but the wall is not going anywhere, so it doesn't matter how much force you apply, right? You're not gonna have any work. And if we use potential energy, then we do not compute the work of the weight force. So that's kind of one thing we did, and that was really important. I'm going to put a star here. You realize that we have choice. Either we can, if there's a change in elevation, that means the object does have a change in potential energy, or also it also means that the weight force is doing work. Okay, but when you apply this in the energy conservation, you have to choose one or the other. You cannot do both of them. Okay, because if you're saying I'm going to keep change in potential energy, then I'm going to say in the work term, weight force work term is going to be taken as 0 because it's already accounted for in the potential energy, or vice versa. Okay, so this is a little bit weird, and I know every year usually students kind of it feels like this is a tricky concept, so I just want to emphasize that, and every time I'm going to explain it in my in the problems when we solve problems. Okay, and next we talked about the again I shared the files with you for Monday. We started talking about variable force. Again, this is the case is that force is not constant, and now we kind of talked about, okay, what are we going to do next? And we looked at the force was F and then half for some distance. That means it's not the same for the entire path. And then again, not just half and half, but then we split it. Okay, it keeps changing. It's changing even more drastically in this figure. So what we said is eventually delta goes to differential, right? We need to add up those in very small distances. So that's what we did, and then we ended up this three-dimensional case. Okay, so this one here was the 1D, and then we generalized it in 3 dimension in this form. So and we don't usually have 3-dimensional cases, but it's better to realize what the general case. So if you have 1-dimensional case, then you're just going to use the first term or whatever. If it's x or y or z, just pick that in the for the problem. And I already posted a video of an example problem using that. This is the next supplemental examples. We usually skip that also. I mean, we always skip that in the class time. I'm going to skip it, but it's a nice problem. Take a look at it. And the next thing is the work by a spring force. So for the work by a spring force, it's really just a specific case of a variable force. It's an example, okay? So it's a good application of a variable force. And we have a spring, as you can see it in the first figure. So x equal to 0 means the object is or the spring is actually relaxed, okay? And then what we did was we are holding this object, and by hand or something and with some external force, we are pulling it away, right? Like you can see that it's been pulled this way. Okay, so there is some sort of applied force pulling it that way. If the object is stationary, you have that applied force pulling it that way. And because of that pull, and the object is no longer in the relaxed position, this is going to feel a force towards the relaxed position. Okay, and this is the spring force. So one thing I want you to realize, spring force is to the left in this specific case, but you can see that the displacement is to the right. Okay, and then this is in the form of X. So what we realize in spring problems, X and Fs, the spring force and the stretch or compress, is always opposite to each other. Okay, so that's kind of interesting. And then we will get a negative sign later on, and that kind of explains why we are getting a negative sign. It's because of these two being always opposite to each other. Okay, but in magnitude, the spring force is related to the stretch or the compress, which is X, in this form, and K is simply a constant, and we call it a spring constant. And this equation is given as negative kx on Wiley, but again, that negative is really just tells you that if you are pulling it to the right, so that spring force is to the left, and it is stretched to the right, so the spring force and the stretch or compress is opposite directions. That's all it tells you. What this is what the negative sign is. Okay, they are opposite to each other. But in magnitude, okay, and this equation is the magnitude equation. It's just simply k times x. K is a number and has a constant of, in SI units, newtons per meters. And it's simply force per length. Okay, that's the dimension. Okay, so x is measured from the relaxed position, so you need to know where x equal to 0 is. Then you can measure your x. You cannot choose arbitrary 0x. You have to choose the 0 to be the relaxed position of the spring. Okay, and it's usually given in the problems. So this relation, this equation, is called Hooke's law. If you heard about the name before, this is what the law, the equation is, and it's a linear equation. So if you plot fs and x, right, in a graph, then the slope will be the spring constant k. Okay, so that's what this is all about. And I think I'm gonna stop it here, and I'm gonna continue in the next video because I don't want to make them too long.